In this lesson, some of the significant performance information that is provided by the flight management computer will be discussed. This will include items like cost index, econ speed, altitude capability, optimum altitude, and the location of performance data in the event of an FMC in-flight failure. Every time you initialize the FMC, you must input cost index. The FMC will use this cost index to compute the most economical climb, cruise, and descent speeds for the scheduled flight when operating in economy mode. For the airline to determine the cost index, they must first determine the factors that affect the total cost of each flight. The factors which affect the cost of a flight can be broken into time-related costs and fuel costs. Time-related costs are any cost which will be reduced by reducing the flight time. This reduction in flight time is accomplished by flying faster climb, cruise, and descent speeds. Simply put, the faster you fly, the lower the time-related costs. For most airlines, portions of the maintenance cost are time-related. For some airlines, flight crew and cabin crew costs are also time-related. Fuel costs are also dependent on the chosen flight speed. There is a certain speed that can be flown which will minimize the trip fuel and therefore minimize the fuel cost for that flight. This speed is determined by the aerodynamics and engine characteristics of the airplane. The goal for an airline is to minimize the total cost of the flight. The total cost would be determined by adding the cost of fuel plus the cost of time. The speed which results in the lowest total cost is the most economical speed for the flight. This speed is called econ speed. Cost index is simply the parameter entered into the FMC, so it can calculate the econ speed for climb, cruise, and descent. If your airline has low time-related cost or high fuel costs, a low cost index is used. This will result in a slower econ speed. If the time-related costs are high or fuel costs very low, a high cost index would be used. This will result in a faster econ speed. Only your airline can gather the information necessary to determine the best cost index for your operation. Typically, cost index is supplied as part of the dispatch papers or is set by company policy. This is the econ climb speed. This is the commanded speed above all waypoint speed constraints, speed restrictions, and speed transition altitudes if economy mode has been selected. This speed will provide the minimum total trip cost based on the cost index entered during FAir econ climb speed. As the airplane climbs to a higher altitude, the climb is flown at a constant Mach number. The FMC will select the Econ Cruise Mach number. This eliminates acceleration or deceleration in the transition from climb to cruise. Once attaining altitude, the FMC will fly the Econ cruise speed. This Econ cruise speed is a function of cost index, gross weight, altitude, and the actual winds. This speed will change during the flight as fuel burns, the wind changes, or a different altitude is selected. This speed can vary from a low of MRC at a cost index of 0 to the VNAV limit speed or cruise thrust limit speed at a high cost index. MRC is the maximum range cruise speed. Flying this speed results in the minimum trip fuel and therefore the maximum range. This occurs at the speed where the fuel mileage is the greatest. Another speed you may be familiar with is LRC, the long-range cruise speed. This speed is defined as the Mach number where the fuel mileage is 99% of the maximum. Flying at LRC results in a 10 to 25 knot increase in ground speed for about 1% increase in trip fuel. On the 777 airplane, LRC is approximately a Mach number of 8.4 when cruising near optimum altitude. A cost index of 140 will approximate LRC. Increasing the Mach number above LRC will significantly increase trip fuel required. For example, increasing the speed from 8.4 to 8.55, about 10 knots, will increase the trip fuel by about 4 to 5% at normal cruise conditions. At high cost indexes, the airplane speed may be limited by the VNAV speed limit or the cruise thrust limit. The VNAV speed limit is VMO minus 5 knots. The cruise thrust limit is the speed where thrust required for level flight equals the maximum cruise thrust available. As temperature increases, the cruise thrust limited Mach number will decrease. At the top of descent, the Econ descent Mach is set equal to the Econ cruise Mach calculated at the end of cruise. As the airplane descends, the speed will change from Mach number control to indicated airspeed control. This speed will be a function of cost index only. Another performance function of the FMC is to compute the optimum and maximum altitude for the airplane. During normal operations, when the FMC is operating in Econ mode, the optimum altitude displayed is the most economic altitude for total trip cost. Therefore, this optimum altitude is a function of cost index and airplane weight. If the airplane is operating in a speed control mode, such as at a constant Mach number or at LRC, this optimum altitude is the altitude which will result in the minimum trip fuel. In a perfect world, the airplane would fly at this optimum altitude in a climbing cruise. But as we all know, ATC will not allow this. Normally, you should climb above the optimum altitude. You would then cruise at this altitude until the optimum altitude has climbed above your current altitude sufficiently to make a step climb necessary to maintain economics. The FMC calculates the best location to make this step climb to minimize the total trip cost. Flying more than 2,000 feet away from the optimum altitude significantly increases the trip cost. Another altitude the FMC computes and displays is the maximum altitude at the current speed. This maximum altitude is based on the more limiting of the thrust limited altitude or the maneuver margin limited altitude. The thrust limited altitude is the maximum altitude the airplane can maintain at the maximum cruise thrust rating, or climb to at the maximum climb thrust rating. This calculation is done with a residual rate of climb of 100 feet per minute. This minimum residual rate of climb can be changed by maintenance. This thrust-limited altitude is a function of temperature. In general, the 777 will be able to go at least 2,000 feet above the optimum altitude up to a temperature of ISA plus 15 degrees Celsius. As stated above, the other limitation checked during the maximum altitude calculation is the maneuver margin. The maneuver margin limited altitude is determined by computing the G margin to initial buffet at the selected altitude and speed. This computed margin is then compared to the airline selected minimum G margin. The FMC will accept G margins from 0.2 Gs, the default, to 0.3 Gs for airplanes certified to FAA standards. For airplanes certified to the CAA and JAR standards, the G margin is 0.3 Gs. If the computed margin is less than the airline selected margin, then the selected altitude is not allowed. A 0.2 G margin is the same as a steady 34-degree bank turn. A 0.3 G margin is the same as a steady 39-degree bank turn. If an engine failure occurs in flight, the engine out cruise page should be selected. If the airplane altitude is above the maximum altitude with an engine out, the airplane can be flown in 3 different modes. If terrain clearance is a potential problem, the engine out drift down speed should be flown. The dispatch requirement for terrain clearance are based on this speed. To be a legal dispatch, The airplane's net engine inoperative performance must be capable of clearing all the en route terrain within 5 statute miles of the intended route by 2,000 feet during an engine inoperative drift down and 1,000 feet after the net engine inoperative level-off height has been reached. The net engine inoperative flight path is the actual drift-down profile reduced by an altitude conservatism equal to 1.1% gradient capability. The FMC will provide you with this engine-out drift-down speed and the predicted maximum altitude on the active engine-out drift-down page. If terrain clearance is not a consideration, the pilot may choose to fly engine-out LRC or a company-defined speed. The maximum altitude calculated will be based on the current active speed, be it drift down, engine-out LRC, or a company speed. If an engine failure has been preceded by an FMC failure, the pilot can get the same data from pages in the Performance in-Flight section of the Airplane Operations Manual. On the 777 airplane, the FMC is required for dispatch. If the FMC performance functions are lost during flight, the pilot can revert to using the performance data in the Performance in-Flight section of the Boeing Operations Manual. This section contains the performance information normally supplied by the FMC. This includes things like engine thrust setting information, cruise data, altitude capability, landing reference speeds, and so on. This performance section also includes landing performance data such as slippery runway landing distance, non-normal configuration landing distance, and brake cooling. This section provides normal all-engine and engine inoperative data for operation with the landing gear in the down position. The charts in this Performance in-Flight section are tabular. The chart is used by entering with the known airplane conditions and reading the desired information. On some charts, the desired information is read at a reference condition and then must be adjusted for conditions that are off reference, as in this example. One last comment on the FMC provided performance. The takeoff reference page provides the takeoff speeds of V1, VR, and V2. These speeds are just like the speeds you are used to seeing in the Quick Reference Handbook. They are valid for a standard balance fuel length takeoff weight. If your airline uses clearway or stopway in the determination of the takeoff weight, the V1 speed would need to be adjusted. If the takeoff is being conducted on a slippery or contaminated runway, the V1 speed is not valid. If improved climb techniques are used, All three speeds, V1, VR, and V2, must be adjusted. In all these special cases, the flight crew must get the takeoff speeds from dispatch.